Alright, so I think we left off somewhere close to here. And I actually think we discussed those two. So this next item, the fundamental theorem of arithmetic claims that every natural number greater than 1 has a unique prime factorization. Does this mean that every natural number greater than 1 can also be created by summing primes? So for instance, let's look at this number 20. 20, if I look at the prime factorization, so I'm going to start dividing by primes. I'm just going to start with the smallest prime first and exhaust it and work my way through the primes. So I'm going to start with 2, and 2 is a factor of 20. It's a prime factor, and its factor pair is 10. So now I'm going to take this 10, and I know 2 is prime, so I'm done, and I'm going to keep using 2 until it's completely exhausted. 2, its factor pair is 5, and I'm done when I have all prime factors. So the prime factorization of 20 is 2 squared times 5, and that is unique. 2 squared and a 5 will only create 20, and that is the only way to create 20 by using prime factors. But if we use primes and addition instead of primes and multiplication, so primes and addition, 20, because I can use prime and multiplication, does that mean I can also use primes and addition? And the answer is yes, because really, I mean, you could argue that multiplication is just repeated addition, so if it works for multiplication, I should be able to make it work for addition, and you can. So 20, I can use the primes and addition to create 20, and I could exhaust 2. So I could do 2 plus 2 plus 2 plus 2 plus 2. I could keep using 2, so on and so forth. And I know that if I do that 10 times, that's going to give me 20. The difference is, if I use addition, it's not going to be unique. So for example, I could use the prime number 17, and I could use the prime number 3. So 17 plus 3 is going to give me a 20. I could use the prime number 5, and 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 that'll give me a 20. So it does not have a unique fingerprint in the way that prime factors do, so prime and multiplication. Primes and addition, there are several ways I can create a 20 using primes and addition, but there's only one way that I can create 20 by using primes and multiplication. So this word right here, unique, is a key word in the definition, probably the most important word in the definition. And because of the uniqueness, this is what allows the RSA encryption to work. Okay, now, so I think we've addressed that. Yes, you can. The answer is yes, you can create any number with the primes and addition and demonstrate the difference. The difference is uniqueness. Okay, now, the divisibility test by 3 claims that to check if a number is divisible by 3 with no remainders, you simply sum each of the number's digits, so apostrophe somewhere in there, and if that sum is divisible by 3, then the number must also be divisible by 3. For example, let's examine the number 42,762. If I take the digit 4 plus the digit 2 plus the digit 7 and sum the digits, it's going to give me 21. Since 21 is divisible by 3 with no remainders, then 42,762 must also be divisible by 3 with no remainders. And I think it was the Vista group that gave us this cool fact. So you can even take the sum 21, So this answer right here, and you can go again. You can take the digits 2 and 1, add them together, and you can keep going and going and going until you get a 3, which implies that it is divisible by 3. But if we kept going and kept going and kept going and we got a 4, then the original number would not be divisible by 3. So justify this divisibility test. Okay, justify the divisibility test by 3. Okay, so here's why the divisibility tests work. So we're going to take our number system, and I've got ones column, tens column, hundreds column, whoops, thousands column, and then 10,000s and so on and so forth. Okay, now we're going to take each of these columns one at a time. So I'm going to take the number 1, divide that by 3, and examine my remainder. So my remainder is going to be 1. I'm going to move the next column over. I'm going to take the 10, I'm going to divide that by 3, and I will observe that my remainder is going to be 1. So the divisibility rules have everything to do with remainders. Okay, I'm going to take my next column over, the hundreds. I'm going to divide that by 3, and let's see, we should have another remainder of 1. And now I'm going to make a conjecture that based on the remainder so far, I'm going to conject that they're going to continue just like this as I divide thousands, 10,000s, 100,000s by 3. So okay, I'm going to stop there. So my conjecture is if I divide each of these by 3, my remainder will always be 1. Okay, now that's nice if your remainder is always 1, because now I'm going to look at this number, 42,762. Okay, so let's change colors. So now let's look at 42,762. And I'm going to write that kind of in an expanded form, so it's going to be 40,000. Well, let's do it this way. I'm going to write it as 4 groups of 10,000. And then we're going to go 2 groups of 1,000 plus 7 groups of 100 plus 6 groups of 10 plus 2 groups of 1. Okay, that is 42,762 written out in expanded form. Okay, now I'm going to examine each of these digits. And I know in my ones column, every 1 is going to give me a remainder of 1. So now I'm just going to tally up how many remainders I've got, and I'm only going to look at the remainders. So if 1 has a remainder of 1, and I got 2 ones, there's going to be 2 remainders. 10, every 10 gives me 1 remainder, and if I have 6 tens, that means there's going to be 6 remainders. Every 100 gives me 1 remainder, and if I have 7 hundreds, that's going to be 7 remainders. Every 1,000 gives me 1 remainder. If I've got 2 groups of 1,000, I'm going to have 2 remainders, 1 for each. Every 10 grand gives me a remainder. If I got 4 of them, that's going to be 4 remainders. And now, if I tally up, if I add all my remainders, if I add the 4 remainders plus the 2 remainders plus the 7 remainders from the hundreds plus the 6 remainders from the 10 plus the 2 remainders from the ones, that gives me a total of 21 remainders. And we suggest that 21 remainders will be the same as if there were no remainders at all. So 21 remainders is the exact same as having no remainders at all. And that kind of led to this idea. If we can agree that 12 is equal to 3 multiplied by 4 plus 0, and 12 is also the same thing as 3 multiplied by 3 plus 3, and 12 is the same as 3 multiplied by 2 plus 6. 12 is the same as 3 multiplied by 1 plus 9, or we could even go the other way. 12 is going to be the same as 3 multiplied by 5 plus negative 3. It's kind of the idea that these are your remainders right here. So the same as 0 remainders is the same as having 3 remainders, or 6 remainders, or 9 remainders, or 21 or 27. And we could go back the other way. Okay, now let's create our own divisibility test for dividing by 4. So division by 4. We're going to go through that same process and see if we can find a pattern. Let's see, ones, tens, hundreds, thousands, 10,000s. Okay, I'm going to start with my ones. Divide 1 by 4 and examine the remainders. There will be 1 remainder. I'm going to divide 10 by 4. Look at its remainders. 2 multiplied by 4 is 8. So that's going to be 2 remainders. 100 divided by 4 is going to be 2. Okay, no remainders. And now I'm going to suggest that as soon as I come across where there are no remainders, that every column to its left will also have no remainders. So for example, there's really no need to divide 1,000 by 4, because I know if 4 goes into 100, it's going to go into every 100. It's going to go into 200, 300, 400, 500, 600, 700, 800, 900, 1000. So just to prove it, 4 times 2 is 8. That's a 5. So that's 20 and 0. So 100 is going to be 10 100s is going to be the same as 1,000. So if in 100 there's no remainders, in 10 hundreds there will also be no remainders. So now, if I look at this number, that same number, what was that same number? 42,762. So if I look at 42,762, okay, I'm going to insert a page. So look at 42,762. Okay, now I'm going to expand that, so that's going to be 4 10,000s. It's going to be 2 1,000s. It's going to be 7 100s. And it's going to be 6 10s and 2 1s. Okay, now I know there will be 0 remainders there. There's going to be 0 remainders here. There's going to be even 0 remainders here. So the only ones I need to look at are going to be, no matter how large or grandiose the number is, the only digits I need to focus on are going to be the last 2 digits. 62. So my divisibility test, I can say, you know what, I'm going to ignore every other digit. I'm just going to look at the last two digits. And if the last two digits, so if 62 is divisible by 4, then 42,762 must be divisible by 4. So if I look at my remainders, this is kind of a tricky thing here. For every 1, there's going to be 1 remainder. And for every 10, there's going to be 2 remainders, and this is kind of hard to remember. The 3 was so nice because it was 1 remainder every single time, but when the remainders start to alternate, it's kind of hard to keep track. So look at this. If for every 1 there was 2 remainders, and I've got 2 1s, so that means there's going to be 2 remainders. And for every 10 there was 2 remainders, and since I have 6 10s, that's going to be 12 remainders. If I sum my remainders, that's going to be 14 remainders. And 14 remainders is not the same as 0 remainders, or 4 remainders, or 8 remainders, or 12 remainders. So I know this is no good. But instead of saying, that's kind of tricky to remember, for every 1 there's 1, for every 10 there's 2, the divisibility test, I'm just going to say this. Just check the last 2 digits, and I think someone suggested that it's got to be even, so it must be even. So if this were a 3, we don't even need to test 63 because we know if it's going to be a multiple of 4, then it must be even. So check the last 2 digits, and maybe it must be even. So I'm going to divide, and if I don't have my division tables memorized, or my multiplication tables memorized beyond 12, you can just test it real quick. 4 into 62, that's going to be 1. So 22, and I know 4 is not going to go into 22. So it will not be divisible by 4. Okay, now our proofs, proof of evens and odds. So prove that 8 is even. And we're going to go with our proof of it can be expressed in 2 equal addends, then it will be even. And we're going to specify that those 2 equal addends must be natural numbers. So as long as I can break this up into 2 equal groups of natural numbers, then we're in business. So 8, I can show that it is even. 8 is even. And maybe just one time I'm going to explain what even is. So maybe at the very, very beginning, you only need to do this once on your test, because if you do it once, we'll use that definition throughout your test. So definition of an even. So I'm going to explain to my audience. I'm going to attempt to show you that this is an even number. But first, for a definition of an even number, if it fits this definition, then it is even, and if I can show it to fit this definition, I am successful. So definition of an even number is going to be any number, maybe well, for now we're going to stick with in your test, we're only going to worry about naturals. We're not going to go into integers and different things like this. So for your test, if you say your definition is any number, and then you got to explain, because there's naturals, wholes, integers. So if you want to say any natural, and then we can build on this definition in the following weeks. But if we're going to stick with the natural, so any natural number, but that's important to tell your audience what kind of numbers you're working with. So any natural number that can be expressed as two equal natural add-ins. So again, it's important to define what kind of groups you're looking for. You're looking for groups that are only from the natural numbers. So for example, if it is n plus n, and that is the exact same thing as 2n. So as long as it fits this model, this is the definition of my definition of an even number in the naturals. So it has to be this quantity plus itself, and if I can show that, then it is even. So 8. If I take 8 and I can show 8 is 4 plus 4, then 8 by definition has to be even because I have shown it into two equal groups. And both those groups are from the naturals, so we're in business. Okay, 9. Prove that 9 is odd. So if this is my definition for even, my definition for the odd can be any natural number. We can stay in the naturals. That can be expressed as two equal natural add-ins with one left over. So it's going to be n plus n. There's always going to be one left over. And that's the same thing as 2n plus 1. So this is my definition for evens. My definition for odds will be almost the same, except there's going to be this one left over. So 9, first of all, you got to force it into, see if we can force it into two equal groups with just one left over, and that's going to be 4 plus 1 is going to be 9. So we're in business. It is odd because it fits my model right here. Okay, prove that 8 plus 6 is even. Let me insert a page. So 8 plus 6 is even. Okay, now my audience, so I'll start off by saying, okay, I'm going to use this definition of an even number. If I can express this quantity as the sum of two equal natural add-ins, then it, by definition, it is even. So 8 plus 6. And we'll do this two ways. We'll kind of do it maybe how Arlie suggested. We'll do it maybe a way that's more friendly to first graders, younger kids, and then we'll do kind of a more maybe of a algebraic approach or an arithmetic approach. So 8, if I take 8 and I'm going to divide it into two equal groups. So 8 is even because by definition I can break it up into two equal groups. 6 is even because I can break it up into two equal groups. And now I used circles for both because 8 and 6 are describing the same thing. This is 8 ones plus 6 ones. So 8's kind of an adjective. It's describing how many. But I think it's important for the kids to understand that 8 is describing how many ones you've got, and 6 is describing how many ones you've got. So I think it could be confusing if we, like, if we're to say stars or something. If I break the 8s up into two groups of 4 stars, and then 6, I break it up into two groups of 3 circles, that kind of implies that 8 is describing a different picture than 6 is describing. But in reality, 8 is describing how many ones you've got, and 6 is describing how many ones you've got. So they're describing the same thing, so I think we should use the same image, the same picture. Because if we use two different images, that's kind of implying that 8's describing 8 something and 6 is describing 6 of something else, since they're different pictures. And because they're both describing the same thing, I'm going to just use circles. So 8 circles and 6 circles. I want to show that it's even. So that was my move number 1. Now my move number 2, I'm going to take these 8 circles and these 6 circles, and if I can group them into 2 equal groups, then it's even. So move number 3. Okay, I am done. I just proved that 8 plus 6 is even, because this fits my model of n plus n, or 2n. And so I'm suggesting right here that each of my n's is 4 ones plus 3 ones. So each of my n's contains 6 ones. So that's a 6 plus a 6. Or that's not 6, I guess there's 7 in each group. So n in this case would be 7 ones. 7 ones plus 7 ones is 14 ones. So it must be even, because I can show 2 equal natural addends. Okay, kind of maybe an algebraic approach. So 8 plus 6 is even. Okay, I'm going to say number 1, 8 is the same thing as 4 plus 4. Move number 2, 4 plus 4 is the same thing as 2 4s. So that's my whole thing right here. Even n plus an n is going to be 2 n's. So I showed that here's my n plus n, and here's my n plus n equals 2n. Okay, number 3, 6 is the same thing as a 3 and a 3. My next move would be to show that 3 plus 3 is the same as 2 groups of 3. And now, my 5th step, I'm going to show 8 plus 6 is the same as, since this is equal to 8, I'm going to substitute in 2 groups of 4, and in place of 6, I'm going to substitute this, 2 groups of 3. Okay, now my next move, 2 groups of 4 plus 2 groups, 2 groups of 3. That is the exact same as 2 groups of 7. My final step, 2 groups of 7 must be even, because I made it look just like this. And I can't remember, I think it was someone in George Washington that suggested we can argue, we can defend each of these steps to a mathematical justification, and that is true, and that's where we're heading in the next few weeks. We're going to introduce the idea of commutative, associative, distributive. We're going to go over all these properties, and when we introduce them, then we're going to link each step to each move. But for right now, we'll say that your proof only has to be linked to this definition right here, definition of an even or definition of an odd. And we'll let you kind of manipulate your groups without really justifying which property your move belongs to. Okay, let's look at a these next couple. Let's prove that 8 plus 7 is odd. So the odd, if I could show that it's 2n plus 1, or an n plus an n plus a 1, then it must be odd. I'm going to do this one just kind of visually. 8 plus 7 is odd, so move number 1, 8. I'm going to break that up into 4 ones and 4 ones. 7 ones, I'm going to break that up into 3 ones and 3 ones, and 1 left over. Okay, my answer, I'm going to try and show that it's odd. And it's odd if it fits this definition. So now I'm going to group. I'm going to create new groups. There's a group, and that group has 4 ones and 3 ones. So this group has 7 ones. And this group right here has 4 ones and 3 ones. So it's got a group of 7. So it fits this, and it fits this, and if there's 1 left over, I am in business. So I just demonstrated that it's odd because I can rearrange it so that it's 2 equal groups of natural add-ins with 1 left over. Okay, let's prove that 7 plus 3 is even. Okay, let's stick with the same kind of approach. Let's do it with manipulative. So 7, I'm going to break it up into 2 groups of 3, and then there's going to be 1 left over. My 3, I'm going to break it up into 2 groups of 1 with 1 left over. Okay, now I'm going to try and force it to fit this idea of evenness, which is 2 equal groups of natural numbers. And if I stare at it, we're going to have to kind of shift some chips around a little bit. So if I kind of look at grouping them how we have in the past, so kind of a group on top and a group on bottom. I noticed that on top I've got a group, or I've got 1, 2, 3, I've got 4 ones, and on the bottom I've got 4 ones, 5 ones, 6 ones. So I've got more ones on the bottom than I do on the top. So if I were to take this chip and move it to the top, that's going to kind of help us balance things out. So I'm going to take this chip up here, put it right there. So now it's no longer there. So now on top I got 1, 2, 3, 4, 5. And on the bottom I've got 1, 2, 3, 4, 5. So I have 5 ones in each group. So it must be even. Because as long as my groups are equal, there's got to be the same amount of ones in each group. Then it must be even. Okay, let's show that 6 plus 4 plus 8 is even. Alright, I wonder if I might have enough space. 6 plus 4 plus 8 is even. Let me insert a page. Okay, now I'm going to try and do a better job and work it out kind of step by step by step by step. Alright, so move number 1. I'm going to use manipulatives to show that 6 ones looks just like this. 1, 2, 3 ones, 4, 5, 6 ones. 4 ones looks like 2 ones, 2 ones. 8 ones looks like 1, 2, 3, 4. So I just discovered that each of these numbers happens to be even because each fits the definition of even. So now step number 2, I'm going to circle, I'm going to create two groups. Circle the top ones and circle the bottom ones. So now it should look like this. 1, 2, 3. And I guess I don't even need to write out what I'm doing, because it's a lot easier to show with the picture. So I'm just going to circle these. I'm going to circle these. And then step number 3, count how many is in each group, and if you have the same amount in each group, you're in business. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 ones in the top group, and there are 9 ones in the bottom. So it looks like this: 9 plus 9, which is looking like our definition of n plus n. So it's got to be even. Okay, now let's look at some examples from kids. What if a kid submits this proof? Shall show that 5 plus 7 is an even number. And they have 5 ones shown with this manipulative. They got little stars. So 5 ones here, 7 ones, 1, 2, 3, 4, 5, 6, 7. Can they have circled 2, 2, 3, 3, and 2. So everything they've circled has an equal amount in them. So here's their explanation. I have circled groups of equal addends, so the answer must be even, because the definition of an even number is any number that has groups of equal addends. And hopefully they're not going to convince you. So they kind of have an understanding of the definition, but not really a solid understanding. So this right here is even because it's 2 equal groups, and this is even, and if you circle these together, they're like 2 equal groups. And kind of the same here for the 7. If you circle the 3 and 3, I mean, these guys are even. But if I just look at this one circle right here, kind of like I looked at the 2, this is odd because there's 3 elements in it. And this guy is going to be the same. So I think I'm just confusing myself, but the bottom line is it cannot be even, but it could be even if they kind of shifted some ones. If they made like a group here and a group here, and as long as you can shift your manipulatives back and forth so that you have the same amount on each side, because we got to have a group of n plus a group of n. So let's look what we got now. Now I got 1, 2, 3, 4. I've got 7 here and I got 5 here. If I were to take this manipulative and put it in the group with this guy, now on this side I would have 6, and on this side I would have 6. So by definition it's got to be even. So we got to create groups and then start shifting your manipulatives from one group to the other until they are balanced, until you got an equal size of groups. And if you can do that, it's even. If you do that if there's one left over, it's odd. So let's look at this right here. Kind of the same thing. So 4, they circled a 2 and a 2, and a 6 they circled 3 and 3. So we got 4 is 2 groups of 2, 6 is 2 groups of 3. So the answer must be even, because the definition of an even number is any number that has 2 groups of equal addends. Okay, now the difference, let's look, before it said the definition of an even number is any number that has groups. And this time we're going to insert the amount of groups. It's going to have 2 groups. So that's kind of a nice thing to see in their definition. But the problem is they don't really have two groups. They have four things circled. So to make two groups, we're going to make what we've done before is we just circled a group right there and a group right there. So now you have two groups. This is group 1 and this is group 2. So group 1 has 1, 2, 3, 4, 5 ones in it, and group 2 has also 5 ones in it. So they just need an extra little bit to prove. So their proof is not acceptable, but with a little work it is. Okay, and this I think might be it. So different numbers, 5 and 7. So they've used manipulatives to show that 5 is 5 ones, 7 is 7 ones. So this is group 1. This is group 2. And if each group has the same number of natural elements, we're in good shape. 1, 2, 3, 4, 5, 6. So group 1 has 6 ones. And group 2 has 6 ones. So 6 ones plus 6 ones looks a lot like my definition of an even. Natural number plus itself. So it must be even. Let's see what they got. 5 is shown as 5 stars. 7 is shown as 7 stars. The top group has 6 stars in it. The bottom group has 6 stars in it. The sum of these two groups must be even because the definition of an even is any number that has two groups of equal add-ins. Okay, that's perfect. And then here is kind of an example of a written out one that kind of more matches our arithmetic approach, our algebraic approach. So prove that 5 plus 7 is an even number. Step number 1. 5 is the same as two groups of 2 plus 1, or two groups of 2 plus 1. Okay, number 2. 7 is the same as two groups of 3 plus 1, or two groups of 3 plus 1. This implies that 5 plus 7 is the same as two groups 2 plus 1 plus two groups 3 plus 1. And two groups of 2 plus 1 plus two groups of 3 plus 1 is the same as two groups of 2 plus two groups of 3 plus two groups of 1. So what we've done is we've taken this one and this one, and we've shown, so this is definition, equals 2n. So we took 1 plus 1 and we rewrote it as two groups of 1. Okay, now two groups of 2 plus two groups of 3 plus two groups of 1 is the same as two groups of 2 plus 3 plus 1. And two groups of 2 plus 3 plus 1 is the same as two groups of 6. So 5 plus 7 is an even number. And that looks pretty good. The only thing, if you haven't maybe put, because it fits our definition, because it fits this, so kind of anchor it back to this guy. That's the only improvement that that proof could use. Two groups, and I guess if you say that at the first, we said before, if you say this at the very first of all your arguments, you don't need to keep repeating it every time. Just say one time, okay, if I can show that it's going to fit this, then I am done with my proof. It will be an even number. But it's always nice to wrap up your argument, even if you are redundant. Okay, the last couple questions. So let's examine the following definitions submitted by 6th graders to determine if they are acceptable. if you find them unacceptable, find a counterexample to demonstrate why. So a sixth grader. An even number is any number that can be expressed as the sum of two equal addends. Okay, now by sixth grade, here's what we're going to be fishing for, is these kids that start saying, well, 5.5 plus 5.5 is equal to 11. Whoops. So I have shown that I've got a group here that is exact same size as this group. So as long as they're two equal addends, then this must be even. So 11 must be even. So that would be awesome if sixth grader were able to prove that 11 is even, if just his definition was as long as it has two groups of equal addends, it's even. Because this just proved that 11 was even. So we got to be picky about what kind of groups are we after. Are we after, and so far here's how we've introduced the naturals, the wholes, and the integers. And 5.5 actually is not found in either of these three number lines. So you're going to have to anchor your definition to one of these, naturals, wholes, or integers. So which one are we going to anchor it to? And we said earlier that if you anchor it to the naturals, that's going to be okay. We are going to extend it to the integers eventually. We're going to say that a -4 plus a -4 is a -8, and we are going to say that this is even. -8 is even. So we're going to get here. We're going to anchor to the integers. So if you want to go ahead and do that now, that's fine. But on the test, what I want you to understand is that kids are going to be clever, and they're going to start to show things according to definitions. So the words we use in our definitions kind of set the parameters and the boundaries for which the kids can play with. So if we just leave it open without defining it to a set of numbers, that kind of leaves it wide open. So the same with this. An even number is any number that can be divided by 2. And we talked about the idea, well, you can divide anything by 2. If I divide 3 by 2, that's going to be 1. Well, I guess 0. There's going to be 1 with 1 left over. So I can divide anything by 2, but the next one, he kind of fishes for this. An even number is any number that can be divided by 2 with no remainder. So that's what this is missing, because I can divide anything by 2, but sometimes there's remainder, sometimes there's not. So this is not a good definition. This one right here is kind of weak. This one is much better. An even number is any number that can be divided by 2 with no remainder. But I mean, check out how important the wording is, because I can take this number, I can take 4.2, and I can divide that by 2, and 2 goes into 4 twice, 2.1, and there is no remainder. So I am saying that 4.2 is even, because it divides by 2 with no remainder. So now you've got to answer, you got a problem here. So we're always trying to look at definitions and see where we can kind of pick them apart, where there's problems. So I want to say any even number is any, so right here I want to explain what type of number. Any integer that can be divided by 2 with no remainder. So for the test, we're just going to make sure you insert what you define, what you anchor this definition to is going to be fine. I don't, if you want to anchor it to the naturals or whatever, but you've got to anchor it to some set of numbers. But ultimately we are going to anchor it to the integers. Okay, this last one, what role does definition play in composing a good proof? It plays probably the most important role. It's a huge role. So if you're going to prove that something is even, you've got to show first the audience that it's even if it fits this definition. Definition of even is 2 equal addends of natural numbers, or 2 equal addends of whole numbers, 2 equal addends of integers. You got to kind of specify the boundaries. And if it fits this, then I have been successful in my proof. So definitions in proof play a huge role. Kind of a cool trivia. Euclid is a Greek mathematician, 300 BC, who very well may have written the most successful and influential text ever in the history of the earth. It is second only to the Bible in the number of editions published. His book, The Elements, consists of 13 books containing definitions and proofs. Abraham Lincoln was very fond of Euclid's Elements. There's some cool stories with Abraham Lincoln and how he studied and used Euclid's Elements in his law practice. And it was because of Euclid's Elements that Abraham Lincoln became great at arguing, kind of practicing law. So that's kind of a fun fact. And then we did this tonight in class, how to find the GCF and LCM of two numbers. And then what do we got? Explain how and why division by primes works, and finding the GCF and LCM, and how it's related to prime factorization. We did that too. So I think we are done. That's the last slide. Email me, call me if you study and you get hung up on something, you got questions, and we'll work stuff out. And good luck in your preparations.